Everyone, November 22nd. All right, today's goal is very simple. I'm going to solve this and then figure out one of the methods. All right, what is this? A sequence of numbers is called arithmetic if it consists of at least two elements, and the difference between every two consecutive elements is the same. So it has to be at least two, and the difference between every two consecutive elements is the same. More formally, a sequence S is arithmetic if and only if this is equal to for all of us. So everybody, okay, that's maybe we have done this before. These are arithmetic. Yeah, so the difference between any two consecutive, any neighboring elements is the same. The following sequence is not. No, it's not. If you're given an array of n integers, nums, and two arrays of m integers each, L and R, represent the m range queries, where the ith query is the range Li and Ri. All the arrays are zero indexed. Return a list of Boolean elements answer, where answer I is true if the subarray nums so from L to R can be rearranged to form an arithmetic sequence, and false otherwise. Okay, so it's guaranteed that Li is smaller than Ri. That's fine. Mn is only 500, so I think the naive solution will work, which is really a naive solution. Well, the naive solution is given any range, we will copy it out, sort it, and then compare, and then check. Which means it's going to take OM and N. OMN. Yeah, I think OMN will definitely work. Well, can you think of a better one? Let's solve this first and then try to see if there's a better one. Okay, so what we're gonna do is int, not int, it's gonna Boolean. Oh no, a list Boolean. Interesting. That's fine. And just for int I equal to 0, L dot length I plus plus. All right, and then we say int temp equals new int Ri minus Li plus 1. And we say for int j equal to 0. No, j equal to Ri. Okay. J is smaller equal to L. Ri. No, wrong. This is L. This is R. And then j plus plus. Temp. Ooh. J minus Li equal to nums j. What's wrong? Manual array copy. Yeah, do you have any other way to do this? System array copy. Ha! System dot array copy. All right, I'll do this. We don't need it. Oh, this. This is an array copy. Destination position way. Why is it the same? Nums. What's array copy? Source array. Source position. Destination. Destination position. The starting point of the destination. Yeah, makes sense. So we're gonna do, this is gonna be 0 and length. Yeah. Okay, so we have temp. Next, we're gonna say arrays.sort temp. Okay. Now after we sort temp, then we have to check. Right? Have to check. Has to be at least 2, right? So when you say int diff shall equal to temp 0, no, temp 1 minus temp 0. Then for int j equal to 2, j smaller than temp dot length, j plus plus. If we can say rest dot add true, right? So we say if temp j minus temp j minus 1 is not equal to diff, then rest dot put should be I, right? Rest dot put. Now wait, hold on, how do we, oh yeah, this false. It's now put dot set, not put. Okay, then we'll break. Otherwise, it will be true. Then we need to return rest. Okay, now I haven't done this before. Okay, naive solution. Definitely work. Naive solution in which we simply copy out the nums subarray from li to ri, sort it, and sort it, and make the and check. I just realized we can make it a little bit faster by not doing this. Hold on. So we get the difference, right? We sort it, and we can just say rest.add temp dot length minus 1 minus temp 0, right, shall equal to, so this minus this is 8, right? And we have 1, 2, 3, 4, which means shall equal to temp 1 minus temp 0, right? And then times temp.length minus 1. And this is minus 12, right? Minus 12. This is minus 4 times 3. Yeah. So we can do that, which means we will not do any of these. So we can go all the way down to 6j. These can be deleted. 7k. And say OMN. Oh, oopsie doozy. Oh, the same as yesterday, pending so long. So this will be faster. Oh no, ON log n. Oh no, it's not right. Okay, save us some. How? How? It's pretty early on as well. So this is not what should be log n. We copy it, sorted it, and then the last minus the first shall be the 1 minus that times its length minus 1. Why is it not right? That is very interesting. One of the false I gave a true. Don't even know which one. Damn it. We'll figure out. Man, it's hard to figure out. Huh? But why? I mean, if only 2, we should still work. Yeah, 2 minus 1 will be 1. Alright, so what we're gonna do is count 1, 2, 3, 4, 5, 6, 7, 8. Okay, we count 8. One, 2, 3, 4, 5, 6, 7, 8. Okay, still there. Hold on. Okay, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23, 24, 25, 26, 27, 30. I think we need to count 30. Well, let's just count 20. Okay, let's just count 20 for safety. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we count 20 out. Alright, count 20 out. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, wonderful. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10. 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, this is much easier. Huh. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I would double check. Make sure it's right. So it's 110 to. Okay, so 110. 110. What is 110? Okay. 110. Man. It's okay. We can do this. Let's do the testing up. Nums. L and R. Okay. Let's include one more. So 110, 24. Doesn't matter. All I want is debug. All right. Temp. Is 9, right? Yeah, 9. Yeah, it's not right. Oh, damn. Yep. Yeah, it's not right because, oh my goodness. Oh my goodness. That is not right. Because someone can go, oh yeah. So, oh yeah, this is not gonna work. Lordy. So is there no other way? It's the only way? Yeah, this doesn't work. I don't know why I thought about it. So what do we do if it just doesn't work? I mean, we already know the naive works. All right, I like to undo. Because I forgot to save the other version. First of all, let's stop this. Okay. Yeah. OM 21. I feel like there gotta be a better way. 36.81%. What do you think? Maybe previous can help us make better decision. Like maybe we can sort L and R. Yeah, we can sort L and R. If we sort, let's say, based on L, so L will be from small to large, okay? So L is from small to large. And then each time we go for the R. Well, the first one we have to check. So each time, so the amount we need to check is reduced. Right? And if it's within the previous, then we can, yeah. Okay, so maybe what we need to do is, no, I don't need this. Let me think. Check. Okay, check. Max extend. Okay, so let's make some change. Call it private boolean check. What do we put? We need to put nums. And then range left, range right. Yep, that's that. Then we are going to copy basically everything to 10 and go back to 13 and paste this. Then we're gonna go to 10. No, go 1. This is range left. No, range right. This is range left. Right, we get a temp, we copy it. Oh shoot, one more. This is range right. This is range left. Right, so we do that, blah blah blah. We don't do this. Don't do this. Basically, we will return here. Right, this one will return false. And we'll return true. Okay, so now what we're gonna do is int max extend, right? Then if your left is bigger than the max extend, then you have to redo it. If it's within the max extend, then from max extend, you work from max extend. Yeah, so like we have the previous, we have extension, right? And your new one coming in, they could have overlap. If they have overlap, then whatever's overlapped, we don't have to do again. So what we need to do is just max extend minus 1, right? That's the range left. We push it in, and then we see if it's correct, right? Because it's overlapping, so whatever previous it has to work for the later. And then if it doesn't work, we still keep at max extend, the max right, because we don't know up to where, right? We don't know up to where. All we know is this doesn't work. And then when you go outside, oh, hold a second. I don't think it works because it's not sorted. It only works if nums is sorted, but num is not sorted. If num's not sorted, if I have the max extent, I say this range works, but the next range, you cannot use the previous result. No, you cannot. You can't. Because whatever is in there might not work. Man, lordy, this is... Let me think again. I don't know another one. Well, what I do know is we might rewrite this, so we can just call it check. Right? We can just call it check. Nums li range left. Then we say okay. I didn't change anything, so I think this is the solution. But like, why? What's the difference between the two? The two are the same. It's exactly the same. Well, we avoid this call. Maybe this call is bad. I don't know. Sort and check. No sorting. I like to see that. What's this no sorting method? Do an array. Okay. Do we just check something plus the difference minus? We don't even know what the difference is. Oh, we do know. So we find a max, we find a min, so we can find a difference. Okay. So just check if each one is in it. Uh-huh. So we need to find min max. How do you find min max? Oh, go through the whole thing. You got a diff. Nice. Nice. Okay, let's try the other one. This is the OMN solution from we find the min and max of the copied array, which allows us to compute diff. Then we use a set to check whether all required elements are in the copied array. Well, the good part is we put a check out, so we don't have to make any change. So we just don't copy, right?
Oh.
So int min equal to nums.0, no nums.0, temp 0. Okay, int max temp 0. And then set integer scene new hash set for int n of temp we say min shall equal to math.min min and n. Max is math.max max and n, and scene.add n. Okay, so if max minus min, we need to put this in mod temp.length minus 1 is not equal to, then we return false immediately. Otherwise, the diff is max minus min divided by temp.length. Okay. Now what we need to do is for everything. Yep. So what we're gonna do is we're gonna delete all of this. For int I equal to 0 i's, so we're gonna do 0 times 1 time smaller than temp.length. Right. smaller than temp.length, I plus plus. If min plus diff times I, we go back. If scene dot contains this, if it not contains, right? If it does not contain, then we return false. I mean, we can, because the min max is definitely in there, right? And we start from min, so what we need to do is just go through, we don't need, I think we can start from 1. So 1, 2, 3, all the way to the end. And we can actually save another one. We can do -1 because the max is also in there. Okay, so with this, we can try. Yep, let's try the other one. So it works. Ooh, it does not work for this one. Interesting. All right, so maybe we have to go, we do this. Oh, very interesting. Oh, I see it. Okay, good. All right, now we're gonna read this simple math solution in C++. We can sort the query and the points by x value, and for query and a point, and for each query, since x is decreasing, wait, hold a second. We sort the query and points by x values, and for each query, so x is decreasing, we just add more points to the candidate set, or qualify y values. We save a map that maps each y to x plus y. Since we're querying the maximum values with y large equal to y prime, the larger the key is, the smaller the value should be. When we insert a key pair in the map, we should trim the map to keep the monotonicity in the map. Does not make any sense. So this sort again, this sort the query. I feel, why do you sort the query? Maybe that's why you don't need. I don't know. Yeah, this one does not explain very well. It's segment tree. Yeah. Oh, hold on. They're using tree map. Are they removing? And they're adding? And they're sorting? I don't know. I don't like this. Because I don't understand. I already use segment tree. What does this map mean? We add qualified points into map. We sort of query. So queries are going large to small as well. So we have a query. Okay. And we add qualified points into the map as we insert new qualified points y and x plus y to the map. We also need to remove all the points to the left with a smaller value. Okay, so when we do the query, if your query is larger than the x, that's a no-go, right? Because you want something bigger than. So okay, so you have the query, and then your check I also need to remove all points to the left with smaller value. query out I can't read C++. Sort queries by x value and also process nums by x value. Keep track of largest y values seen so far in a queue in a binary search for the result. Alright, we'll sort a reverse sort query. I have the index reverse, that's cool. Rest is default dict, yeah, that's fine. D, what the hell is D? It's ABJ in Q. What the hell is I? I smaller than line X. And XI 0 is larger or equal to A. Larger or equal to A. Okay. If xi1 is larger than max y, we update max y, the max y encountered so far. And then while d append max y. Huh? Max? We keep track the max y encountered so far. So x is going down. Okay, we have some y value. So query is also x going down. So what if my query x is larger than this x? It depends. the monotonic array. The monotonic array. Monotonic array. So we have the x and if this is smaller than this, and if max y encountered so far, max y encountered so far. Okay, so this is the max y. So x is always max x, right? It's always maximum x from large to small. And as we go through the x, okay, as we go through the x, we have a bunch of y values, right? And what we want is to keep track of the largest y value. Largest y encountered so far, right? So we have a y value, and if the current one is within, I mean the first one definitely go in, right? X and a y, and x plus y, right? So next come up for the next query. We'll check if x is larger, then we compare y. And if y is bigger, then it's -1. If y... Yeah, but why don't you compare x? X can be bigger than the biggest. We put all the x in. And each time we put the x in, we compare the y. We compare the y. And once we have one, yeah, because the query is also going down. So x is always going to be right, except from the beginning, right? Except from the beginning. So we get rid of the x at the beginning, which is bigger than the biggest x. The query x is bigger than the biggest x. So we get rid of those, right? Now the first one, and every x will work. So we don't have to worry about x. So when x comes in, we check, right? It's smaller, yeah, it's always going to be, well, if it's larger, then we go into the yes. If it's larger than the current I, then we go into the y to check the y, because the current x is not big enough, but there will definitely be some x bigger than you. Yes. So as long as we check the y, we're fine. So if it is smaller, right, then we compare its y, right? We compare its y. And what we want is the current bigger y. So it's a monotonic decreasing array for the y, right? Decreasing array. That's not true. It's not for the y. It's not for the y. It's just we'll keep track. Lord, what are we keeping track of? The y is increasing. The y is increasing. What? Oh, man. So we have a bigger... So we encounter a bigger y. I mean, that makes sense, right? You want to encounter a bigger y. And you'll push it in. And you get another bigger y. But with a smaller x plus y, you also push it in. But if I have a bigger x plus, so yes, we only want to keep track. We want the biggest y. Yeah, we want a bigger y. So that's why we keep track of the bigger y. But if I have an x plus y is bigger, so we want to pop the smaller, because every time we do this operation, the y gets bigger, right? So the only time we do is we get a bigger y, right? We get a bigger y. We don't need max. We can just, yeah, I know. So we just get a bigger y, we get a bigger y, we get a bigger y. But when you get a bigger y, your x plus y might not be bigger because x is getting smaller, right? Your x plus y may be small. So if your x plus y may get small, we still maintain it, right? So we have a bigger y, which means your y is increasing, okay? And your y is increasing, but your x plus y may be, you know, if I have a bigger one, so x plus y is decreasing, right? X plus y, because if I have a bigger one, it will pop, so it will always be decreasing. So if I have a bigger one but I have a smaller, yeah, I have a bigger one and a smaller. So eventually it's like this. So when we query, x would definitely be correct. So we just query for y, right? So y, we find a spot. So yeah, this is your biggest value. So you cannot go left, you can only go right. So this towards the end is the biggest value. So by doing this, we ensure everybody is sorted. X is sorted, y is sorted, x plus y is sorted. So y and x plus y is in a monotonic stack where y is going up, x plus y is going down. Since y is going up, right, every time we do binary search, get a point, we want to know. And then because x plus y is going down, so this point is the smallest point, is the largest x plus y, right? And also since we sort the queries, the query goes down. And yeah, the query goes down. And we can binary search. Exactly. Binary search. So if binary search give you the result is 0, that's no good, right? Binary search give you the result 0. That means you are nothing is, no y is bigger than you. Wait, hold a second. Binary search. No, binary search, go to the rightmost. Right, that means nothing. Nothing is bigger than you. Huh. Okay. 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 Makes sense. No, I'm not gonna implement it today. I'll sleep on this and then try it again tomorrow. Yeah, I'll try again tomorrow for this. This is good. This I don't need. This is the segment tree. Yeah, it's all right. Okay, we'll try this tomorrow. I'll see you guys tomorrow.